that's available in the system, and the polymorphism, in other words, the ability to work with any different types that's inherent in the sending of messages. And what this does is it makes code much more reusable. It means that you can have generic code throughout the system in some superclass that can be used by all of the subclasses. And it greatly factors the code in your system. You can then add messages to subclasses or override them. For instance, here's an object called a pin that might have some little program in it to draw a line for a certain distance and then turn a certain angle for doing some geometric design. You could define a subclass of that called a commander, which would do all the same things, but which might actually own a whole set of pins itself, so that when it was told to draw a line of a certain length, it would tell all of its sub-parts to draw lines of different lengths. And you could make really fun designs that way. And then you could define another class below that called the collider, which would do a kaleidoscopic type of pattern. And the only thing you'd have to do would be to override the turn operation so that the sub-pins would turn opposite directions for every other pin, and you get a kaleidoscope effect. And all of this is done without having to write any new code in the subclasses except for what's different. And you can also make use of the code that you've overridden. For instance, in initializing this commander, it can invoke the initialize code that's inherited by its parent by saying super initialize. This is kind of a pseudo variable. It's like sending the message to itself, but using the definitions inherited from above. And then it can put in its own particular code as well that it wants to be done for initialization. So in this case, it would initialize itself normally, and this fan-out operation would be one which would take all the sub-pins. Instead of all starting in the same direction, it would spread them all out. Another point that I'd like to bring up that I think of as a part of object-oriented programming, although it's probably not a strict requirement, but it certainly is a complexity issue, is automatic storage management. If a system doesn't have automatic storage management, it inevitably has all sorts of code sprinkled throughout it dealing with the lifetime of storage. And it's code that's it's easy to get the code wrong, so it's hard to do it properly. It doesn't tell you anything about the problem that's being solved. So in that sense, it's irrelevant detail. And if it's wrong, it will cause the system to crash most terribly. So I just think that if we're going to talk about what it means to be object-oriented, I think we have to assume that the language is high level to begin with, and I think of automatic storage management as being a requirement for any high-level language. I'd like to talk just a little bit about the operating system interface, which is another area that's important in object-oriented programming languages. Because if you try to bolt object-oriented semantics onto a conventional operating system, you can have problems at the interface that really detract from the overall value of having an object-oriented programming language. And I think what you need to do is to have the point of view that the operating system itself is just a collection of objects. And there are all sorts of objects like files and directories that this kind of programming is perfect for modeling. It's good for modeling the display. And then the one thing that the operating system gives you is a certain number of primitive operations which presumably are either necessary to get at the hardware or that run particularly fast. And what you have to do is to be very careful in how those are interfaced to the rest of the programming language so that all the requirements of the operating system are met when you finally call it. And if there's a failure, for instance, if you call some operating system routine for turning a rectangle black that requires integer coordinates on the rectangle, you better be sure that you have just integers by the time you do that. But you don't want to reflect that requirement out into the whole programming system. You want rectangles to be able to have floating point coordinates and fractional coordinates. So what you have to do is to check that on the way in and use the object-oriented protocol to find out the integer coordinate, pass that on to the operating system. And that way, you can get the result you want without having made things ungainly for the programmer. I have sort of a simple test which I consider how you find out if a system is truly object-oriented. And it's, can you define your own new kind of number, for instance, a fraction? And you'll have to define how the plus operation works and how the less than comparison works and all that good stuff. But once you've done that, can you use one of your numbers in a rectangle that's a part of some program that you're writing to do graphics, and then tell the operating system to blacken that rectangle and have it all work? And what it requires is that all of the operations that want to get done are done by sending messages, and moreover that you can add your own new kinds of messages and have them work. And the key to this is that you need uniform reference. In other words, everything is an object. And the only way you can do anything is by sending a message to an object. And what this guarantees is a property which I call simulation, which is if you only have a hold of this object by a reference and you can only send it messages, then you're sort of guaranteed that somebody else can come along and put a completely different kind of object out there, and everything that you've written will work because you don't know anything about it. All you know is what kinds of questions it can answer properly. Now, people ask, is object-oriented programming just good for graphics? The answer is no. It turns out that graphics is a great application for object-oriented programming. And the reason is that graphics consists of a whole family, kind of an algebra, of similarly behaving objects. For instance, there are atomic objects or primitive ones like points and lines, text and bitmaps. And then there are higher level objects like rectangles or ovals or polygons that are made up of smaller objects. And then there are really complicated, or at least really high-level ones, such as overlays. You might have an overlay and it overlays 50 different other polygons, or a window which represents a clipped representation of some graphics. But these all will obey the same message protocol. And you can put them all in a hierarchy and they'll all inherit the same properties. So it's a domain which just factors itself out very nicely this way. And it's interesting that the application of graphics is one where that has in the press has been called object-oriented when you talk about graphical user interfaces. And I think that's just because the kind of operations that you do with the screen are very much like the operations you do inside of a real object-oriented programming system. There are lots of other tasks for which object-oriented programming is effective. For instance, building compilers. If you look at compiler construction as a task where you're generating a tree that corresponds to the parse of some linguistic statement, you can model that tree perfectly that way. You can have a node that represents an expression, a node that represents a method, a node that represents a message. And the compiler simply builds this tree, and then each node will have local properties, local methods for generating its own kind of code. And that's how you would generate code for something you're compiling. Or it can have code for printing back source code that corresponds to it, and you can use that to do a pretty print of some code in the system. It can also have methods in it for locating the PC. And if every node in your tree has a way to locate where the program counter is in it, then you can find the program counter in a large method. And you can use this then in the debugger. And you can also have other methods for printing the structure that you've compiled into another language, and that way build a translator. So that's another area that just breaks down perfectly this way. And there are many others. Airline reservation systems, banking systems, all can be factored nicely this way.